Okay, so this actually turns out to be our last video. You must be blooming with excitement. All right, and so there are a couple more formulas, right? So a couple more identities that actually come up. The addition formulas proper, not so much, but the double angle formulas often come up enough so I should really talk about them. And so the natural thing first off is if I had to take the sine of a sum, so if I took the sine of x plus 3 pi, let's say, the natural instinct people seem to have is to distribute the sine through the sum, right? So you can't do that, as it turns out. It's not a linear function, what that means. So for instance, to prove that that wouldn't be true, suppose I just take A to be 30 degrees and B to be 60, right? We know that the sum is 90 degrees, and so the sine of the sum is the sine of 90, which is 1. But if I took the sine of A and B separately, sine of 30 degrees is a half, sine of 60 degrees is radical 3 over 2. And so if you add those guys together, you do not get 1 back. And so apparently the sine of A plus B is not the sine of A plus the sine of B. It doesn't hold. But that's not to say there aren't formulas that help you to compute the sine and cosine of sums and differences like this more easily, using the sine and cosine of just the individual values. Right? In fact, there are, right? So there's something called the addition and subtraction formulas. And if A happens to be equal to B, like here, if they were true, that would be the sine of 2A and the cosine of 2A. Those are called double angle formulas. So those are special cases of the addition formulas. So we're going to start off with this guy. And I'm not actually going to work through the derivation with you. I really want you to remember, I'd like you to read it, but talking you through it really is just going to take us a longer time than I need I need this video to take for you. I want you just to take away the double angle formulas in the end. And so cosine of A minus B, you can prove just using the distance formula down below and some rotation ideas that this is equal to cosine of A times cosine of B plus the sine of A times the sine of B. You can actually prove that using what I have done there. Okay. And so also, the minute I know that, so the minute you prove one of these, you have the other ones. And here's why. This is the other one. So the cosine of a sum is the same thing, but with a minus sign. The reason for that is I can always view a sum, the A plus B, as a difference, right? In other words, A plus B is really A minus a negative B. I have a formula that enables me to compute the cosine of a difference that was derived above, right? And so what I'm going to do is I'm going to view cosine of A plus B as cosine of A minus a negative B. I'm going to apply that difference formula here, right, with A is A and the input is negative B. And then I'm going to apply the even and odd identities, right? We know how those behave. Cosine of negative B is just cosine of B. Sine of negative B is negative 1 times sine of B. And so I can rewrite this last term as negative sine of A sine of B. All right, so we have that formula. This one is a translation result, right? That we kind of observed this before. We know that cosine of pi over 2 minus b is the same exact thing as cosine of b minus pi over 2 because cosine is even, right? But if you remember, I said cosine and sine look pretty much the same. It just one slid over a little bit. Well, it's actually that little bit happens to be pi over 2. To prove that, we'll just use the difference formula. We know that cosine of a difference, we have a formula that we used here to prove this other result. Just apply it at this point here. So I'm using this formula with A equal pi over 2 and B is just B. If I plug in pi over 2 for A, I know the cosine of pi over 2 is 0, so that term drops out. And then sine of pi over 2 is 1, so that term remains. And so indeed you get cosine of pi over 2 minus b is equal to sine of b. All right, and you can do the same sort of thing for the sine of a difference, right? Once you actually have that formula for sine, you can prove it the same way. Okay, and so those are called the complementary angle identities, the co-identities. Okay. All right, so here we're going to use this identity, the first guy here, to help us out with this. What do you mean? Well, let's actually look. Sine of a plus b is the cosine of pi over 2 minus a plus b. Right, that's what we said here. Sine of beta is equal to cosine of pi over 2 minus beta. So whatever I put here, if I subtract it from pi over 2 in input for cosine, I get the same thing back. So I'm going to do that. And now I'm going to shift, I'm going to distribute the negative sign through, right? And then I'm going to just group those first two together. Everything's being subtracted, so I can certainly do that. And now I'm going to apply the difference formula for cosine, where the a is now pi over 2 minus a, and the b is just b. If I do that, I get that expression, but now I'll use the co-identities again to get that cosine of pi over 2 minus a is sine of a, and the sine of that guy is cosine of a. And so in the end, your addition formula for sine of a plus b is sine of a cosine of b plus cosine of a sine of b. Okay, and then if you use a similar trick here, you can derive the corresponding addition formula for sine of a minus b. All right. Of particular interest here are the double angle formulas. And so let's take a look at these. The sine of 2a is 2 sine of a cosine of a. But what I'm going to use here is this formula for sine of a plus b. In this formula, a is equal to b, right? And so sine of 2a can be written as sine of a plus a. And by using that addition formula for a sum for sine, I get sine of a cosine of a plus sine of a cosine of a. That's 2 sine of a cosine of a. So that actually works out. And then you can do the same thing. I'll let you try this one before you read on. But the cosine of 2a, I'm going to use the addition formula for cosine. And what I'll end up getting is this difference. Okay, so if you do that, using the addition formula for cosine, you in fact do get that result to work. Okay, I'm not going to have you responsible for proving these, by the way, on an exam or whatnot. I'm just trying to show you where they come from. But what you do want to at least have in memory are these two, right? Even the co-identities aren't as important, and the general addition formulas you can always look up. But these guys here occur often enough where you should really remember them. Okay, and then I'm going to, don't worry about your turn 1. Your turn 2 we should look at. All right, so let's look at your turn 2 together. Okay, so we know that suppose the sine of theta is minus 5 over 6, and suppose the theta's terminal side now is in quadrant 4, right? So in quadrant 4, remember the cosine is positive. What I want before I start computing these quantities, what I want is to find the cosine of theta, because I'm going to need them both. And so use the Pythagorean identity just like we did before, right? We're going to put negative 5, 6 in for the sine of theta, square that, subtract it from both sides and take the square root. But remember, the theta has a terminal side in quadrant 4, and so the cosine is positive there. So cosine of theta is radical 11 over 6. All right, so now if I want to compute tangent of 2 theta, by definition, tangent of 2 theta is the sine of 2 theta over the cosine of 2 theta. But I have those two double angle formulas that we just looked at, right? Namely, the top is 2 sine of theta cosine of theta, and the bottom is the difference of those squares. Okay? The thing to note here is that this entire expression involves just knowledge of sine of theta and cosine of theta, both of which we have, right? We're given negative 5, 6 for sine and radical 11 over 6 for cosine. And so if you plug those in here and simplify, in the end you get this result. Okay. The key identity, or the key note here, is that you're using the identities to simplify an expression in such a way that you can use the information that you have at your disposal to compute it. That's the point. Okay, here, if I want the cosine of theta minus 3 pi, be careful. Remember, cosine is periodic, but with period 2 pi. And so here you can't just say this is equal to cosine of theta, because this is not an integer multiple of 2 pi. Remember that integer multiple business is really important. And so what I want to do here is use the difference formula for cosine, right? So we know that it's cosine theta times sine 3 pi plus sine theta cosine 3 pi. Sine of 3 pi is 0, and cosine of 3 pi is negative 1. And so in the end, this actually simplifies to minus sine of theta. And I know what sine of theta was. It's minus 5/6. And so I get 5/6 back. All right, and then finally for this guy here, cosecant of the difference. Well, by definition of cosecant, it's 1 over the sine of that difference. And I have a formula for the sine of a difference, right? Sine of pi over 3 cosine theta minus cosine pi over 3 sine theta. I know how to compute the sine of pi over 3 and the cosine of pi over 3 just using the unit circle. So I plug those in, and then I just simplify the bottom, right? Those are just fractions. You simplify that guy to get this expression. Okay, so these problems are very similar to ones we attacked before, but now you can attack more elaborate quantities because we have more identities at our disposal. You can continue doing this with half-angle formulas and whatnot as well. Again, that's not our point here. I just wanted to have some basic exposure to these formulas, in particular the double angle ones, so that when they pop up, you can deal with them. All right, so there's only a few homework problems here. Give those a shot and let me know how that goes. Okay, bye.